Welcome back, Algebra Express. We are in Rockswold 5.4. We're going to start talking about logarithmic functions today. And so last time we were talking about exponential functions. And so we are only a few lessons away from the end. And just one more test. It's a two-parter, but one more test. And 3 more lessons. So we are almost there. But here we have what we talk about. The common logarithm is going to be the first thing that we talk about. So typically when we write numbers, we write numbers in decimal base. So we really like to do log base 10 a lot of times. And so since we do log base 10 a lot, if you see a log and you don't see a base there, you can kind of always assume it's going to be a base 10. So like on this, if you wanted to write a base 10 on this thing, you could write maybe a small 10. If you look forward, we can have different base logs. Like here's a log base 2, here's a log base 3. We're going to start talking about log base 10. And let's talk about log base 10. We want to talk about the exponential function that has a base of 10. And so from the previous section, this first function should be something that is hopefully doable. If we do 10 to the minus third, that's the same thing as 1 over 10 to the positive third. It's the same thing as 1 over 3 zeros, or 1 over 1,000. Positive 3 looks cool. So if I plug in a minus 3 into here, I'm going to get 1 over 1,000. If I plug in a minus 2, I get 1 over 10 into squared, or 1 over 100. This is going to give me 1 over 10. If I plug in 0, I get 10 to the 0. It's going to give me 1. We talked about it previously when we have an exponential. If we raise something, any base, besides 0, if we raise any base to the 0, we're going to get 1 out of it. So typically we will get this point 0, 1 when we have an exponential. The other thing is that we have 1, 10 to the first is 10. 10 squared is 100, 10 to the third is 1,000. Okay, if you want to convert these decimals to now we want to look at this thing. And it tells us right here, the logarithm is the inverse of the exponential. So we've talked about how to find inverses and how to do them with 1 over 1,000 here. And if I take a log of 1 over 1,000, and again, this is a log base 10, that's going to give me minus 3. So I can do this sort of mechanically with what I know from my inverses. One, two, three. And so this is an inverse of exponents. So the way that we're going to kind of think about these is by thinking about exponents backwards. So if we look at this, this is log base 10. So this is like saying if I have a base 10, what exponent would I need to get 1 over 1,000? I would need the exponent of minus 3. If I have 10, that one might be an easier one to do. If I have 10 and I'm talking about a base 10, what exponent is happening here? This is the same thing as saying 10 to the first. This is the same thing as saying what? 10 squared. This is the same thing as saying 10 to the third up here. So if I rewrite these as base 10, the question now is, what exponent would I need to get to this number? So the property here is this is log base 10. Some people like to do a little simpler. This is my base, this is my exponent, this is the result it's going to give me. Okay, so they leave a box in here, they're leaving a box as their variable. So if you want to put a question mark in there, you can put a question mark. If you wanted to be a little bit more maybe algebraically savvy, right? Probably put like a Y or something in there. That would also work. So log of 100. So if we want to do log of 100, we want to know what this is equal to. We can rewrite this as asking like what 10 to the what power is going to be 100. And if we do this one I think might be sort of obvious. 10 squared is going to give me 100. So log base 10 of 100 should be this thing right here, or the 2. Okay, so I want to look at the same thing, log base of 1 over 1,000. Log base 10 of 1 over 1,000 equal to what number? So this is like asking 10 to the what power is going to be 1 over 1,000. One over 1,000, this has 3 zeros. And it is going to be a negative because it is on the bottom. And so if we want to know log base of 1 over 1,000, this is going to give me a -3. And if I'm looking at this last one, this is like asking 10 to the power is going to give me 1. And so 10 to the 0 power should give you 1. Okay, so this is sort of one way we can go about it. We can go about thinking about what power of 10 do we need to get there. If we rewrite these things, we could rewrite these things. So log of 100 is log of what, 10 squared? And this is a log base 10. The other way we can write this is log base 10 of 10 to the minus 1 over 1,000 is 10 to the -3. And the last thing is log base 10 of, instead of 1, I'm going to write it kind of a silly way as like 10 to the 0. So you might notice we are getting the exponent out of this thing. Looking along here, I'm getting this. And so what is happening with these? They are inverse operations. So I'm plugging the 2 as an exponent of 10, and then I'm taking a log base 10. These things are inverse operations. So we're going to get to, I think, maybe on the next page. But the other way you can do that is by writing these things as a base 10. If you do that, you can get this as 2, 3, and this one is a 0. And those are the same solutions we got. So you can do it either with this property, or you can rewrite the thing as a base 10 and take the inverse property. Okay. The next thing they're going to throw at us is an application for decibels. So decibels and sound intensity are a exponential logarithmic sort of scale, sort of relation between the two. I believe if we increase decibels, it increases the sound intensity by factors of 10. Sound intensity is measured in watts per centimeter squared. Hearing range is about 10 to the minus 16 to 10 to the minus 4th. The decibel scale converts the units so that hearing range is between 0 and 120. Sound levels and decibels are given by this. So this is the important little tidbit they're giving us here. This is the function to find decibels. Given X is our sound intensity. And so they want us to look at this. They want us to plug a few things in. There are a few properties we might have to go back over here. If we want to plug in, the first thing is what? 10 to the minus 12 into this thing. It's 10. And this 10 is a coefficient on the outside. So this is like 10 times the log. Formula. And I'm multiplying by 10 to the minus 12. So this, I'm definitely going to want to use some exponent properties to clean this up a little bit. This is 10 log base 10 over here. And I have 10. Now, if I multiply like bases, I have to add the exponents. So 16 plus a minus 12 is like 16 minus 12 to the power of 4 here. So if I'm looking at this thing, ten to the what power is going to give me 10 to the 4th. This should be giving me 4 out of this thing. So if I do log base 10 of 10 to the 4th, it should be giving me 4. And now I'm doing 10 times 4, and so this should be giving me 40. And I'm talking about decibels here. So this gives me 40 decibels. Now I want to look at 10 to the minus 8th. So if I plug in 10 to the minus 8th into my formula, this is 10 times log of 10 to the 16th and 10 to the minus 8th. So we should get a similar sort of thing here happening here. This will be log, and I have like bases. I can add those exponents. 16 minus 8 is going to give me 8. If I look here, this is log base 10 of 10 to the 8th. This thing should be giving me 8. I want to know if this thing was a base 10, what would my exponent be? It is a base 10. It's got an exponent of 8. So log base 10 of 10 to the 8th should be 8. And this is going to give me 80 decibels. I know there are slight variations of the decibels scale system, depending what application you're using it for. Okay, so now we want to start talking about other bases. So besides base 10, we can have other bases. And what this is telling me, if I look at something like a log base 2 of 8, what I should be thinking is log base 2 of 8 is equal to what? I should be thinking about 2 to the what is giving me 8. And so it should be 2 to the third is giving you 8. So since 3 is my exponent here, log base 2 of 8 should be giving me 3. So it is the same property, but we're doing it with different numbers is all we're doing now. We still do this sort of property here. We go 2 to the question mark is giving me 8. 2 to the third will give me 8, so my solution must be 3, which was my exponent. Same thing here. Log base 3 of 1 over nothing equal to, so I'm thinking about 3 to the what power is going to give me 1/9. 1/9 is kind of like 1 over 3 squared if you wanted to do that. And so this is sort of like a 3 to the minus 2 power. And so since 3 to the minus 2 is my exponent, this thing is a minus 2 here. And now everybody's favorite character here. 8 to the what power? Give me 1. So 8 to the 0 should be giving me 1. You might notice something similar when we take a log base of anything and we do log of 1, right? If I did log base 8 here, it'd be 8 to the 0 gives me 1. If I did log base, we did log base 10 already. Make it something else, log base 3. What would my solution be here? 3 to the what power is going to give me 1. If I did any base here, whether it's 3, whether it's 10, whether it's 8, you might be noticing that this will always be 0. So anytime we take a log base 1, it should be giving us 0. And I think that's coming up in a second. Maybe it might even be the next section. Okay. So we talked about log base 10. If you don't see a base on your log, you can always assume it's a log base 10. We talked about logs of different integers, positive integers. And now we want to talk about this log base e. So when we did exponentials, we did some things with base e or Euler's number. And so now we want to talk about the inverse of this. So this is the natural exponential. This is the natural log. And so if you see ln, you can do ln if you did log base e on your calculator. That is the same thing as doing ln. That is what that thing means. It means the base on our log now is that e or, that natural exponential. And so they give us a few examples to get over this. Okay, so now they're giving us radicals, and we've brushed kind of like briefly on it, but if I see a radical here, we talked about putting a 2 there if there's no number there. But if I wanted to rewrite these, I'm going to go ahead and rewrite these off the top here. So this would be sort of like a 10 to the 1/2 power. Too much, I talked about it briefly. These would be like I'm doing them to the 1/2 power. Okay, so if I see something like ln e to the 5, this is sort of like a base e here. So e to the what power is going to give me e to the 5? E to the 5th power. If I see 1 over a to the 5, so they're trying to get you to sort of generalize these things like this. If I see 1 over a to the 5, another way I can rewrite this is a to the minus 5. What this is going to end up giving me when I get these fractions like this are negative exponents, and they're going to end up giving me negative logs. If I look at log base 10 of 10 to the 1/2, I'm thinking 10 to the what exponent is going to give me 10 to the 1/2. 10 to the 1/2 will give me 10 to the 1/2. Same thing here. If I have an ln of e to the 1/2, this should also be giving me 1/2. Okay, so now they want to talk about this inverse sort of property. And so we have been sort of using this property. This is sort of, if we rewrite it, you can see the property there of the definition of the log, right? So if we do log of what, a of a to the x is equal to x. So we've been kind of skimming past this thing. But if you do your own circle, we're going to get a to the x is equal to a to the x. Sort of using and skimming through this property. This kind of follows from that definition of the log that we were previously doing. Again, if we have something with log base, what, 10 of 10 to the, I don't know, half is what we had previously. We can look at this log base 10, and this 10 is my base. And these sorts of things right here are inverses. So what I'm really concerned with is that half coming off of there. The other way looks a little bit weirder. And so the other way is saying something, if I have like 10, the log of what I can do here is I know log base 10 and 10 to the something being exponentiated are inverse functions. So this thing and this thing are going to inverse themselves, and it will give me back whatever is getting plugged into my log up here. So that's sort of how they look with base 10. If we look here, this is what it sort of looks like with a base 5. So if I see this 5 and I see it's being raised to a log base 5, what I can do as being simplified out, right? They are inverse functions, so 5 into log to the 5. Those things are inverses. So what this should end up giving me is the 3 that I was plugging into my log. ln and e raised to the power. So my ln and my e should be simplifying out. If I simplify out my ln and my e, what is left over is an x plus my 10 and my log base 10 are inverse functions. So if I raise a log as a base 10, exponentiate a log with a base 10, those are inverse functions. What I should be left over with is what I was originally plugging into my log, which was my x squared. Okay. So we have done a table with log base 10. So now they want us to look at a table with log base 2 and they want us to graph a table. Okay, so I want to recap. Let's go back and look over here. 10 to the x. So if I do a 10 to the x, and I want to do an inverse of 10 to the x, what might that inverse look like? So we've done inverse functions. Inverse functions should be reflective about the y equals x line. So if we wanted to reflect it about this line, you can do that. There may be some like notable features to talk about when we talk about 10 to the x here. So if we look at 10 to the x, if we go left into the negative numbers, we can plug in negative numbers into here. We can plug in positive. Our domain here is all real numbers when we talk about 10 to the x. But our range goes from 0 to infinity. So here, it's got this sort of horizontal asymptote happening here. It's got a horizontal asymptote happening at y equals 0. So if we think about the other one, it should have a vertical asymptote at x equals 0. Come on. There we go. Let's do green. There we go. And so maybe some key features. It's got a vertical asymptote at x equals 0. As it goes to the left, it's shooting off to minus infinity. So if we get a fractional number, that means we had a negative exponent. So the smaller the fraction, the larger the negative on the exponent. And you might notice our domain for our inverse is like the range for our original function. So if we're looking at the domain on our logarithmic functions, it is going to be, we cannot plug in 0. We haven't done that yet. We can't plug in 0. We will talk about why in a second, but we're not plugging in 0. We can plug in fractional numbers, and we can plug in 1 will give us 0. That was the thing that we talked about. Anything to the 0 power will give us 1. So 0, 1 or 1, 0, sorry. 0, 1 is this one. And this one is 1, 0. So this is because anything to the 0 power is going to give me 1. Is why I'm getting this one. And the same thing here, right? Anything to the 0 power, 10 to the 0 power is going to give me 1. And this thing, it goes up and it goes off to infinity, right? This goes off to infinity really drastically. This guy is sort of like the tortoise over here. He is going off to infinity, but he is not going off to infinity very fast. Logarithmic functions grow really, really slowly. Exponential functions grow really, really fast. Okay, so we want to graph this thing probably by hand. And if we're going to do what, 1/8, we're probably going to have to guesstimate a few points. But it'll be all right, as long as it's a good sort of shape for a graph. 1/8, 2, 0. So we probably have sort of an idea of what it's going to look like based off of log base 10. If I go to 1/8 in my x, I'm not going much out in my x, but I'm going to go down 3. I'm going to go up to 1/4, and I'm going to go down 2. I'm going to go up to 1/2 and go down 1. I'm going to go out to 1 and goes to 0. I'm going to go out to 2. I'm going to go up 1. I'm going to go out to 2, 3, 4, and go up 2, 4, 5, 6, 7, 8 is this last one, and I'm going to go up 3. So I plot the points. I swap the points. I plot the points, and I draw my graph. So I've talked a little bit about it, but This guy's got a horizontal asymptote at y equals 0. This guy should have a vertical asymptote here at x equals 0. So there is a vertical asymptote here. You should not go past it. We never touch. It's like annoying your younger sibling in the back seat, right? I'm not touching you. Okay. This is log base 2 of x. And just to reemphasize, let's go look at it on Desmos and compare and contrast to maybe log base. We don't need this guy here anymore. We don't need this guy here anymore. If we know 2 to the x and we want to flip it, it's going to look something like that. Let's get a different color on this guy, blue. And let's compare just these two. So they have similar sort of shapes. They have the asymptote at x equals 0, and it shoots off to infinity. I think the log base 2 actually shoots off to infinity a little quicker than the log base 10. Okay, so we want to talk about the domain, and you might notice they're not even doing log base 2. They're just saying of logs in general. What is going to be our domain? And I said it, but we cannot plug in 0. So if we want to talk about a log of 0, why can we not plug in 0? Why does this not work? What is this going to give us? 10 to the what power is going to give me 0? If he can solve this one, I'm not sure why you're in this class. You should be doing some higher math or something. I don't think you're going to solve this thing very easily. If we think about 10 to the 0 power, that gives me 1. If I put 10 to the any power, right? Anything 10 to the first power is going to give me 10. Maybe you're thinking about fractional powers. I don't know, 10 to the 1/2 is the same thing as the square root of 10. I'm going to have to bust out the calculator to figure out what the heck this is, because it's not rational, but it's definitely not 0. If you want to do negative powers, that's going to start giving you fractions. So if you can figure out a power to raise 10 to where it's going to give you 0, you're doing better than a lot of us, because I don't think this is going to happen. This is going to be undefined. It does not exist. So one of those words, not defined in the current system, it does not exist. So what is this telling me? This is telling me 0 is not in my domain on this function. So I cannot plug in 0. Can I plug in anything larger than 0? Like really, really small fractional numbers. I've done it before. But I can do stuff like this. I just have to count the zeros. This is a -5 here. So I can plug in fractional numbers. It's going to give me negative numbers when I plug it in fractions. My domain, and hopefully we can see it on the graph as well, we're not including 0, but we're doing anything larger than 0. So 0 and on to infinity. When I talk about my range on this thing, my range, this thing goes all the way down. This thing shoots off to -infinity here. This thing, it's the tortoise. It goes up and up. It goes up slowly, but it goes there eventually. It keeps going to infinity. And again, if we think about, I'm going to do a rough sketch of what 2 to the x would look like. It goes through here, and stuff like 4, and then 3. Take a little off now. It was going to be a rough sketch. So if I think about 2 to the x, and I think about this guy's domain and range, It's the flip of this thing, right? What can I plug into an exponential? I can plug in anything from minus infinity to infinity. What is it going to spit out? It's going to have this horizontal asymptote at 0, and then it's going to keep going up. Okay, so now they want you to graph a log base 3 of x plus 5. So before I did this, I would probably do an x 3. And I would probably try to pick out my numbers so that they come out in a pretty sort of way. Two and 3. All right, so now that I have this table made, I would flip the table to get log base 3. Now that I have my original table made, and this is just following the steps that we did on the previous one, right? So now I want to do y equals log base 3 of x. I want to do a table for this. So how do I do that table? I do 1 over 27, and that's going to give me minus 3. I do 1 over 9. That's going to give me a minus 2. 1/3 is going to give me a minus 1. I plug in 1, and it's going to give me 0. So make sure you get those in the right order. And plug in 3, it's going to give me 1. I plug in 9, it will give me 2. I plug in 27, it will give me 3. Running out of room here. Okay. Okay, so if we wanted to plot, and I'm just doing log base 3 now. I'm not doing what they're assigning here. They're doing an x plus 5 in here that I got to count for in a second. But if I want to plot this thing, I think it might be beneficial just to plot this thing first. So this is x is 1/27, and I'm like down here at a minus 3, something like that. So I barely go out, and then I go down 3. I go out 1/9, which isn't going much more, and I go down to minus 2. And I go out 1/3. I go out to minus 1. Not too far along here. And then I go out to 1, 1. Out of here. 9 and 2, something like that. It's got this shape. And so this would be my log base 3 of x. Okay, so now if I want to draw log base 3 of x plus 5. Now I want to talk about what this x plus 5 is doing. And we should be getting this from like our graph shifts. What's happening to my x or y quantity is hopefully the first thing you're asking yourself. This plus 5 and is like right there on the x. So it is inside the log, it is inside the parentheses. So we are going to do plus 5 before we start taking logs of things. So it's happening inside, it's happening to the x. So adding 5 to the x, it is going to happen sort of the opposite of what you think it's going to happen. I want to move this thing left 5 units. So I have an asymptote here at x equals 0. So if I move this left 5 units, I'm going to have to go along here for 1, 2, 3, 4, 5. Now I got this asymptote happening along here. And so I'm moving each of these points left 5. Oh, here. So this should be going through -4. And I'm going out, what, 9? 7, 8, 9. I think that should give me a previous shape for my graph. Close here, but this is not going to pass an asymptote. And the host point connection with these points should look something similar as that. And this is log base 3 of x plus 5. It's the same graph moved to the left 5. And that is the final graph 2 graph on this thing. All right, so I will see y'all soon. Only 2 more left after this. Stay tuned.